because there was a glitch on my part and I forgot to record the assignment for Monday. I am going to, that would have been Monday, class 27. If you missed this class, you missed AL8 and some homemade cinnamon rolls that Olivia Stevenson was kind enough to make for me. And so I'm sorry about that you did miss that. I would have been happy to distribute to those that were here and happened not to be. But anyway, I'm going to go over and cover basically what I did then, so you can watch this and be updated on what we covered. This was an addition. This was something I inserted just because of this, the earthquake in Myanmar, which is the old Burma, and this was taken from March 28th. I've got a couple of sources going here that I put together about this. We talked about earthquakes. This isn't part of this system. This lesson series is earthquakes. We had that last time, but I thought this just reinforces something I've said, and I think it'll make a difference. If somebody ever mentions earthquakes, you have something that can click into your mind, hopefully, and let you think, oh, I kind of know something about that. So in this particular earthquake was in the area of the one that we studied for the earthquake in the Indian Ocean, the tsunami generated earthquake, and megathrust earthquake and resulting tsunami. So this is the same area as the Indian plate moves under the Eurasian plate. So it's moving forward and it moves under the Eurasian plate. Well, on the side of that, on the right side of that plate movement, there's some transform faulting going on. So it's pulling along this other piece with it as it moves forward to subduct. It's pulling across another part, and that part is a transform fault. And that's what happened to this. This is what happens to this fault, the earthquake in Myanmar. So the subduction below Myanmar is very oblique, meaning that the oceanic plate is sliding under Myanmar with a lot of sideways motion directed to the north. To accommodate all the sideways motions, faults have formed that allow tectonic plate slithers to move sideways, so they're moving sideways. And they're called transform faults, as hopefully you remember. And the Saguenay fault is one of them. That's the fault that this earthquake occurred on. And it's the same type of motion that we find in the San Andreas Fault in California. That's a slip slide transform fault. It builds up energy. There's force on it to move, and it's stuck together. It doesn't move and doesn't move, and finally it'll break free, and you'll get an elastic rebound, and you'll get this one plate shifting suddenly forward. Well, that's what happened here. This Saguenay fault is very long, 745 miles long and very straight. So the straight of it means earthquakes can rupture over large areas. And the larger the area of the fault that slips, the larger the earthquake. So there have been 6 of these large earthquakes of magnitude 7 or above in this region in the last 100 years. Earthquakes on transform faults with continents can be particularly destructive, as the earthquake rupture can be very shallow, causing a lot of shaking at the surface. Because the reason is, shock waves are not dissipated as they go from the focus of the earthquake to the surface of buildings. They're not dissipated over long distances. The shallowness of the earthquake means they get there quicker without being disrupted by a lot of material. So, or changed or transformed as they go through material. So buildings thusly relieve shaking's full force, and their continental nature means population centers can be located very close to the fault, which was the case in this. This Myanmar earthquake, the Saginaw Fault runs close to Mandalay, the second largest city in Myanmar, with 1.5 million people. So this second largest city is very close to this fault. It's got 1.5 million people. And the quake had a magnitude of 7.7, which is significant. And it was only 6.2 miles deep, which means it was really shallow. So the shaking was intense. Not only that, but at 10 minutes after this quake, there was an aftershock of 6.4, which itself is a significant aftershock. So many buildings in Mandalay were built some time ago, so were not designed for earthquake resistance, and a number crashed to earth under the violent shaking. And this is just a review of something that was asked on your second exam. Lots of damage and loss of life will occur. Why? Because it was a shallow quake, a shallow transform quake. It was a large magnitude, resulting in lots of surface shaking. It was close to a densely populated area, generally poor construction material and practices, with no warning and accompanied by a strong aftershock. So there were things that contributed to the seriousness of this earthquake. And so in Bangkok, Thailand, about 680 miles away from this quake, the shaking resulted in fear, structural damage, and fatalities. Construction on a deep, very soft soils of the underlying geological features of Bangkok. Also, the ground motion amplification experienced by these tall buildings on unstable ground, these conditions were well documented in Bangkok. So when the shaking from this quake traveled 680 miles to Bangkok, it was hitting a place that soil was just right for accelerating the shaking. As we mentioned, the San Andreas Fault, there was shaking that would decline until it got to the Marina District in San Francisco, and it was built on fill, and so the shaking accelerated as it got there. Well, that's what happened here in Bangkok, and they had some destruction happening there. So this isn't going to be on a test, but I thought it was interesting, something we just covered this, and something on our world, and this is what I was hoping to do with this class, at least bring something that is relevant, so at least you have an idea of what might be going on when they call these things, not just watching buildings fall down, but actually having some idea about what went into this thing. So now I'm going to get to the lecture of Monday. And we covered a couple of things. I'm gonna post this so you have it, but I thought I'd give you a video of it to cover it for those that the async class and for those that missed it in this class. So we're talking about galactic cosmic radiation, GCR. It comes from outside our solar system. It's not generated from our sun. We're going to talk about, well, I already did this class just before that I'm going here. We talked about the sun and what it does, but these galactic cosmic radiation comes from usually within our Milky Way galaxy, but outside our solar system. Our solar system is here, a galaxy. We're just one of between 100 and 400 billion, there being 100 and 400 billion stars. Our sun is one of those stars, But within our solar system, rays are coming outside of our solar system from the interior of the Milky Way galaxy. And generally, galactic cosmic radiation is composed of nuclei of atoms that have had their surrounding electrons stripped away. So they're neutrons, or they're nuclei that had electrons, but the electrons have been stripped away, and they're traveling at the speed of light, these little guys. Nearly. Now, what I'm gonna cover here, there's some notes in red you might see on the screen. Just a note, a lot of these things, they hypothesize, they don't know why exactly. So they're hypothesizing. These particles were probably accelerated by magnetic fields of supernova remnants, but not the supernova that exploded itself. That's what they think. They're not sure, but that's what they think. So it's okay for a scientist to not be sure, as long as they're saying that they're not sure. Pretending that they know it's true absolutely when they don't is I don't think it's honest science. You cannot know a lot, and you don't get a demerit for not knowing. But anyway, the giant expanding clouds of gas and magnetic fields that remain after a supernova can last for probably thousands of years. They don't know for sure. During that time, cosmic rays are probably accelerated inside them. Not sure. Could be. Trying to figure out how they get where they get. Why all the electrons would be stripped off and just have the nucleus just traveling forward at near the speed of light. They're trying to figure that out. They're speculating it could be happening like this. It seems to make sense, but they don't know for sure. It's okay. So, as they travel through the very thin gas of interstellar space, some of the galactic cosmic radiation interacts with gas, this interstellar gas, and emits gamma rays. And the detection of that reaction is how we come to the conclusion that GRC passes through the Milky Way galaxy. That these things are coming through the galaxy, and the ones that we're concerned about are the ones actually that are heading toward our solar system. GRC is extremely damaging to materials and biology. In general, we're largely shielded from GRCs, or GCRs, on Earth because of our planet's atmosphere and magnetic field. So our magnetic field that comes out from the North Pole and the South Pole, forms a ring around that magnetic field, and our atmosphere. Because our upper atmosphere does a lot to absorb these things. It takes them out of the angry push toward where we are in the lower atmosphere of this planet. Our upper atmosphere does a lot to take out these cosmic, galactic cosmic rays, or radiation, so rays. Anyway, the moon, for example, is not shielded from GRC, doesn't have any atmosphere, GCRs, because it lacks a global magnetic field and atmosphere. So it doesn't have an atmosphere, it doesn't have a magnetic field, as far as we can tell, and so they can just bombard it, and that's what they do. And we'll read something about that as I go on with this. In summary, GCR is heavy, high-energy ions of elements that have all had their electrons stripped away as they journey through the galaxy at nearly the speed of light. They can cause the ionization of atoms as they pass through matter, and can pass practically unimpeded through a typical spacecraft or the skin of an astronaut. GCR are the dominant source of radiation that must be dealt with aboard current spacecraft and future space missions within our solar system. Because these particles are affected by the sun's magnetic field, their average intensity is highest during the period of minimum sunspots, when the sun's magnetic field is at its weakest. So when you've got sunspots, I'll talk about that in the following next lecture, but the sunspots generate, well, solar energy, plasma that goes out, and it partially, it does act as a barrier out on outer limits of our solar system. It forms kind of a barrier for incoming galactic cosmic rays. So when it's weakest, when there's less solar activity, you'll get resultingly more galactic cosmic rays coming in or entering our solar system. When it's stronger, they'll be correspondingly less. Because the GRC is difficult to shield against, it occurs on each space mission, is often more hazardous than solar particle events. Okay, now this is following up on this part, space radiation in the lives of the Apollo astronauts. So these were ending in the early 70s, late 60s, early 70s. A new study, and that new study was in 2016, has revealed that a troubling number of lunar astronauts from NASA's Apollo program, ending in the early 70s, are suffering high mortality rates due to heart disease. The cause? Possible exposure to high levels of deep space radiation during their trip to the moon. So these astronauts in the late 60s, 70s, went outside of our Earth's atmosphere, outside of the protection of our magnetic fields. They went outside of that and went to the moon. Well, then they were exposed to galactic cosmic rays that they wouldn't have been otherwise had they stayed within the atmosphere. So these are pictures. There's a picture of the takeoff. Atlas is taking off a space capsule. They're on their moon, and then they're returning from the moon, and they're waving at the happy crowd. So since the end of NASA's celebrated program that saw men walk on the moon for the last time in '72, human spacecraft has been limited to low Earth orbit. That's where the International Space Station is, in a low Earth orbit, inside the Earth's natural shielding from high levels of cosmic radiation. So they're in a low level so they can be shielded by our magnetic field and atmosphere from these cosmic radiation. The study compared mortality rates of lunar astronauts who passed away to astronauts who never flew, and those who have only made it to orbit, low orbit. The number of cardiovascular disease-related deaths among the deep space astronauts were significantly higher. I don't have the statistics on that, but that's why these rays, and they go beyond our atmosphere and our protection with that, and that's why they're reducing their flight, not just to flying around out there. There are things that they've got to take care of here. So that was this first part. Okay, and one other part. So this will be, I thought I had it up here, but I'll get it for you. Here we go. So, this is the sun. And the sun, this is just a superficial covering of this particular star. It's about 93 million miles from the Earth on average. It gets a little closer, a little farther away, but about 93 million miles average. Takes a beam of light, traveling 186,000 miles per second. It takes that 8 minutes and 20 seconds to travel that distance. That's the speed of light. That's what it takes light to travel that far. So when light comes from our sun, it's old light. It's been traveling already for 8 minutes and 20 seconds before it hits us. So we're seeing old light. If we're looking at places that are farther away, like if you're looking at Saturn out there, and you see its rings, well, the reason you see is the sun has reflected off the material the rings are formed from and is coming back. I forget how many minutes that takes, but the sun's light travels to them, reflects back off them, and in our eye, and I don't know how many minutes it takes, quite a few minutes. So we're seeing really old light. It just is what we're doing. Anyway, the sun is the largest object in our solar system, but it's only classified as a medium-sized star in the main sequence of stars. And the main sequence of stars, if you might remember, are those stars, the Hertzsprung-Russell diagram on some page in the 700s of our textbook. You'll see that, and the main sequence of stars, basically, their size is related to their luminosity. I think size and luminosity are corresponding. But you get some that are not main sequence, that may be very large but very cold, or some that are very small and very hot. So they're not the main sequence, but this is a medium-sized star. Our sun is composed of four general layers: the corona, which is the outer atmosphere; the chromosphere, which is the lower atmosphere. So there are two sections of atmosphere: an upper, which is the corona, and a lower, which is the atmosphere. The surface is a photosphere. That's the surface of the sun. And the surface of the sun, I think, is about 6,000 to 10,000 degrees. The chromosphere is hundreds of times hotter than that, but it's a lot less dense. And then you have the core. So these four general layers are not defined. They're not a specific, they're not a little definition about them, because the sun's gaseous nature, it's a quarter of the density of the Earth. You don't have sharp boundaries. So there are no sharp boundaries delineating the corona from the chromosphere, from the photosphere, from the core. There's not. The sun, however, is 1.25 million times the Earth's volume. So it's a lot bigger. Radiating energy in the form of both light and heat. That's what it's doing. Both light and heat are being radiated for the sun, that travel in waves of differing lengths and frequencies. Okay? The maximum wavelength output from the surface of the sun, originating from the photosphere, its surface, is approximately 500 nanometers. Now that's in the blue-green light range, not violet, but blue-green. And actually it varies. The majority, the largest part of wavelength output, not the only. It radiates from radio waves to gamma rays. It radiates at the whole range, but the largest part of the range it radiates is in this greenish area from roughly blue to green range, 483 to 520 nanometers, that part of visible light, depending on the temperature used to represent the surface of the sun, which is not defined clearly. So calculations are done doing Wien's law, and this is, you should know about what this law is, what it does. The temperature and lambda, the wavelength, which radiates most strongly. So you find out what wavelength is radiating most strongly from a star. Our sun, for example, it's in the green range, and so it has a nanometer. Let's say it is 500 nanometers. So the temperature, this is in kelvins, the temperature in Kelvin, this is temperature in degrees Kelvin, is equal to approximately 3 times 10 to the 6th divided by the nanometers of the dominant wavelength that it's radiating. So if this was 500, you divide 500 into this and you get the temperature. Now, if it was operating more in the red range, if that was the dominant, not just a radiant part of the radiant energy, if it was the dominating measure of radiant energy, would be, let's say, in the red range, so it'd be 700. Well, if you divide a fixed number by a larger number, the temperature is going to go down. You're dividing a bigger number, 700, into this number, is going to give you a smaller temperature than if it was only 500 into this number. That'd give you a larger one. So that calculates, if you use 500, for our sun it calculates to about 6,000 degrees Kelvin. That's the surface, that's what's operating on the surface. So that's, we use a value of 3, I've used it here, but it's actually 2.898. So this is what you need to know. The longer the maximum wavelength, the lower the temperature. The longer the maximum wavelength, the lower the temperature. If the wavelength is shortened, meaning it's hotter, the temperature will rise. Longer wavelength, lower temperature. Shorter wavelength, higher temperature. That's what you need to know from that. And that class is in sum. I went over a couple other things, but one of them, because the async class, I didn't want to put out observation 3 until it's been completed by everybody. I talked about that one, and I will talk about that one probably in our the class period after today's, and discuss that with y'all. So there you have it. That's the review, and God bless you. I hope you have a great week. Well, it's not a weekend yet. This is only Wednesday. So, a great Wednesday. God bless you.